In this module, I want to go through a few examples for proving results with mathematical induction. Here is the first example. Let Pn be an expression that says it's 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 all the way up to 2 to the power n. We want to show that this is equivalent to 2 to the power n plus 1 minus 1. Again, we want to prove this result by induction as a way to learn induction. So even though you may be able to prove this result without induction, I don't want to go there right now. So let Pn be the corresponding predicate. Our goal is to now show this by proof of induction. So we are going to have 3 steps. The first step is basis for the smallest value of n. In this case, the smallest value of n that we care about is, the reason is we want this result to be true for any non-negative integer n. That means the smallest integer we care about is 0. So we want to show that p0 is true. So let's see why p0 is true. So we substitute n is equal to 0 in this expression. That means the last term that we would want is 2 to the power 0. And that means we will have exactly one term, namely 2 to the power 0. So now once we figure that out, we can see it's 2 to the power 0, that is 1, which is also 2 to the power 1 minus 1. Our next step is to assume that pk is true for some arbitrary k, and then we want to show that pk plus 1 true is true as well. In this proof, where we are showing pk logically implies pk plus 1, once again k is an arbitrary value. We are not going to assign it a particular value like 5, 7, etc. So here is the proof. As I said earlier, what we want to do is find the expression for pk in the expression for pk plus 1. So pk plus 1, the term that we have is 2 to the power 0 plus 2 to the power 1 all the way up to 2 to the power k plus 1. If I look at this term over here, this is what I find in p of k. So essentially, we are going to find this term and then replace it by what we have assumed with our hypothesis. So we are going to substitute this to be this value is substituted by this value, which is 2 to the power k plus 1 minus 1. This term is going to be left as is, as 2 to the power k plus 1. Now we can do some math. 2 to the power k plus 1 plus 2 to the power k plus 1 is 2 to the power k plus 2. And that's exactly what we wanted, which is 2 to the power k plus 1 plus 1 minus 1. This implies that p of k implies p of k plus 1 for any arbitrary value of k. Now here is another example. Here we want to show that 2 to the power n is greater than n cube for all values of n greater than or equal to 10. Let's look at the proof. Again, we have 3 steps. The first step is basis, where we are going to consider the value of n to be the smallest value of n that we care about. So the result was expected to be true for n greater than or equal to 10. That means the base case is going to be for n is equal to 10. In this case, we have 2 to the power 10, which is 1024, is indeed greater than 10 to the power 3, which is 1000. So now let's assume that this result is true for some value of k, or we can use strong induction to assume that this result is true for all values equal to or less than k. Now our goal is to show that 2 to the power k plus 1 is greater than k plus 1 to the power 3. So now what we have to do? What we have to do is, I can see that inside 2 to the power k plus 1 I can find the term 2 to the power k, and I can see that I can use 2 to the power k plus 1 is 2 times 2 to the power k. Inside k plus 1 cube, finding k cube is a little bit more challenging, but if we push through our proof, we would be able to do that, and that's something that I'm going to do in this step over here, and I want you to notice it as we complete this proof. Okay, so this is what we have. We're going to write 2 to the power k plus 1 as 2 times 2 to the power k. I'm going to keep this term 2 to the power k as is, and I'm going to substitute this value 2 by this expression 1 plus 1/10 to the power 3. Now where did this come from? This came from sort of an innovative idea that we needed to make so that we can find k cube and k plus 1 cube a relation. So here, first of all, let's observe that this result is actually true, and it is true because 1.1 to the power 3 is 1.331. That is definitely greater than, that is definitely smaller than 2. The next part is we are going to replace this 1/10 by 1 over k, and we are adding the term here greater than or equal to, and the reason we are able to do that is because k is guaranteed to be greater than or equal to 10. That means 1/10 is going to be greater than or equal to 1 divided by k. Once we did that, we are going to use our induction hypothesis, and we are going to change this 2 to the power k to k cube, and while we do that, we can change this relation to greater than. So that means our next step is going to be 1 plus 1 divided by k to the power 3 times 2 to the power k is greater than 1 plus 1 divided by k to the power 3 times k cube. And this is exactly the term that we needed, which is k plus 1 cube. In general, when you have induction used for inequalities, you need to do more work. You need to do some sort of innovation because you have to somehow relate the inequalities to one another. When you're doing induction for equalities, generally you can let algebra do the work. But for inequalities, you need to identify some sort of an intuition, and the intuition here was I wanted to get this term 1 plus 1 divided by k to the power 3 because that will let me relate k cube and k plus 1 cube. And to do that, I needed to get this intermediate term, and that intermediate term was sort of an innovation required to make this proof work. Here is proof of mathematical induction as to why it works. So in chapter 1 we studied how we write proofs. So essentially in mathematical induction we have a bunch of hypotheses, namely p of 1 is true, and for any k, p of k implies p of k plus 1. Our goal was to show that for any n, p of n is true. So let's see how we can do this proof by contradiction. We first start with the contrary assumption, that is not of for all n p of n. Now we can use De Morgan's law to push the negation in. Then we have a negation of p of x for some x, so that means we can take existential instantiation to say that p of r is false for some r. Now this is one of the things that we can do, which is we can say, well, I don't want any r, but I want the smallest r that is possible. So in this case, r is the smallest value of r for which p of r is false. By choice of r, p of r minus 1 is true. P of 1 is true by our premise. That means r has to be greater than 0. And now we can use our other premise, which is for any k, p of k implies p of k plus 1. We instantiate k is equal to r minus 1 in this case to get p of r minus 1 implies p of r. From this we can conclude using p of r minus 1 and p of r minus 1 implies p of r, that p of r is true. And now we have a problem because statement 9 said that p of r is true, statement 3 said that p of r is false, and it can't be simultaneously true and false. Let's continue with one more example. Here we have h of j, which is defined as the harmonic number, and our goal is to prove this result, namely h of 2 to the power n is greater than 1 plus n divided by 2. It's greater than or equal to 1 plus n divided by 2. Here is the proof. We have h of j. We want to prove this for the base case. For the base case, j is equal to 0. So that means I have the term h of 2 to the power 0, which is h of 1. That means the last term that I want is 1 divided by 1. And in this case, this sum that I have is 1. And I want to show that it's greater than or equal to 1 plus 0 divided by 2. And in this case, it is true, 1 is in fact greater than or equal to 1. Now we are going to assume that this result is true for some value of k, and we want to show that it is true for k plus 1. So let's see what we have here. What is the relation between h 2 to the power k and h 2 to the power k plus 1? The relation is that this term has few extra terms. In fact, it has quite many extra terms. What is the relation between this one and this one? The difference here is, the relation is that this number over here is exactly half larger. So we want to now relate these extra terms to the value half. If we are able to do that, we are golden. We will be able to complete the proof. This intuition is important before you start writing the proof, because that will help you to make sure that whatever you're doing is for a specific reason, and that will help you make the proof work right. So here is the proof. As I said, we first find this term, which is where we can use the inductive hypothesis. These are the extra terms over here, and as I said earlier, our job is to relate this to half. So first of all, we can replace this expression by this expression because those two are essentially the same. Then we are going to leave these extra terms over here as they are. Next, I'm going to use the inductive hypothesis to replace this by greater than or equal to 1 plus k divided by 2. These extra terms are as is. And finally, we are going to relate these extra terms to half. So we can observe how many terms are there. I start from 2 to the power k plus 1. I end with 2 to the power k plus 1. So that means we have a total of 2 to the power k terms. This last term is the smallest term among these terms. So if I replace each of these terms, each of the terms in here by this smallest term, then I would have a greater than or equal to, but I would be able to do that, and in that case this value would be 2 to the power k divided by 2 to the power k plus 1, and in fact that is exactly the value we are looking for, which is half. Once we get this half, we do a little bit of algebra and we are able to prove this result. I'm going to ask you to pause the presentation here for a little bit so that you can go through each step again to make sure that you understand what's happening. The two main things that happened was we replaced this term by this and then subsequently by the term 1 plus k divided by 2. The second thing that we did was we got these extra terms, and because we wanted to show this result as greater than or equal to, we replaced each term by the smallest term that we had, and that allowed us to get it to half, which was what we wanted to do, because that was the difference between 1 plus k divided by 2 and 1 plus k plus 1 divided by 2. I want to add a few notes about inequality problems and using induction to solve those. As I have said before, in general, the goal of the inductive step is to find p of k in p of k plus 1. P of k plus 1 is an expression when p is evaluated for k plus 1. We need to find the corresponding expression for pk inside that. Now, if the problem we are working with is an equality problem, then essentially once we find p of k in p of k plus 1 and substitute based on the inductive hypothesis, then the problem just boils down to algebra, and we need to sort of push through it, the algebra part, to get to our final answer. With inequality, we need some more work because simply substituting doesn't always work. Now, the following approach works for many problems, most if not all the problems that are discussed in this class. And some of the things right now will appear a little bit abstract, so I want to look at one example of this on the next slide. So in an Inequality-based mathematical induction proof, the inductive step will be of the form some term A is greater than some term C. Now, what we're going to do is we're going to use the inductive hypothesis to show that A is greater than some term B, which is slightly different. Essentially, what we're going to do is we're going to find P of K in P of K plus 1. And when we do that, we will get some term like A, which is the term from our inductive step is greater than some another expression B. Now, in order to complete the proof, we would need to do B is greater than C. That would basically be just some sort of algebra generally. Now, finding P requires some sort of innovation. Now, in some cases, you would be able to do that simply by looking at the inductive hypothesis and seeing what you get. Most of the time that would be just right, but sometimes you may need to do a little bit more innovation to find P. So I want to revisit this earlier proof and I want to describe what I mean by A and C again. So here, this is what we have to prove. So this I'm going to call A, this I'm going to call C, and the goal of the inductive step is to show that A is greater than C. Now what did we do here? What we did here was we found P of K in the expression for P of K plus 1, and in particular it was this. So this is what I'm going to call my beta. Now what I got here was I got A is greater than B because of what I had in the inductive step, which is I substituted this term for this term. That was something I got from the inductive hypothesis. So this is going to be my B term. The rest of it now was showing that B is greater than C, and that basically boiled down to showing that this is greater than half. And that's exactly what we did here. I want to emphasize the key to understanding induction is to solve many problems. We will do a lot of these problems during the homework, but this is going to be very important to make sure you have understood induction well. We have reached the end of the module, so I would like you to do the review quiz at this time.